All right, and then tonight we've got 12 people coming over for dinner. So I have to be there. My wife will kill me. So you wouldn't have a professor tomorrow if I don't show up. But tomorrow I'll stay as late as you need. So I'll stay till midnight or 1 a.m. or whatever. So you won't be able to get in, but I'll maybe, but you just bang on the door and I can hear you. So if you really need help and you're desperate, we can still work on it tomorrow. But what I think maybe I'll do, so let me just say a couple things. So Thursday we're going to have, we're having demo day, so it's coming right up. And so kind of how that'll go down. So I want, if you can, if you don't have a class before, then I'd like you to come, and get set up as early as you can. If you have a class right before, then fine. If you've got several people on your team and maybe one of them's not in class or whatever, then see if they can get it, start setting it up. We will have 18 tables and, no, we'll have more than that. Yeah, maybe 20 tables and 20 blackboards or cork boards. And I'll have push pins. So I want you to have at least one piece of 8.5 by 11 paper that you can stick up on your board, and it gives the number of your team, your group number anyway, and then the names of the people on the team, and kind of the title of your project. So that's all you have to have. If you want to put other things up, you'll have half of a bulletin board to put them up on. So you should be able to do that. And then you'll also have half of a table. Okay, so hopefully you can fit your project within half of a table. If you need more than that, let me know. We might be able to squeeze 3 people on one table and have some project with a large apparatus have their own table all by themselves. But so we can work that out. So hopefully I'll probably be down there. I'll probably go down there by 2 and just kind of hang around. Although typically what happens, there's still some last minute help that needs to be had. So a lot of times I'm kind of in my office trying to get that done. But I'll ask Ann Schul to be there, and hopefully she'll help kind of get things organized in the atrium. So I'll try and be in my office most of that time. So if you still need help, you can come and we'll do some last minute work. So a couple of things. One, let me just say a few words about, so you really need to organize, I know we've talked about this, I talked about this a little bit last week, but I really want you to think, one of the skills that you need to be working on, and the reason why we do this project is, I want you to, because up till now, most of the labs, there's still stuff you have to do, there are challenges and stuff, but a lot of it kind of gets spoon-fed to you. And then your lab, there's lots of help. And so, but when you're doing a project on your own, you really have to do some original design work, right? You have to kind of think it through. And so there's some principles to kind of think about. And so let's talk about those a little bit. So first off, it's really smart to get your logic figured out. So first of all, you have to work on your logic. And that is the steps in the software features that are required to make your project work. And for some things, that can be complicated. Like there are several groups using the membrane pad where there's 16 keys. You have a little membrane pad, and it's got like I forget, like 0, 1, 2, A, 3, 4, 5, B, 6, 7, 8, C, and then star. I think it starts with 1 anyway, and 9, and then there's a pound sign and B, something like that. I think the 1 and the 9 are switched. The 1 and the 0 are switched. This is 0, I think. But anyway, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0 at the bottom. But anyhow, and then there are 4 wires that drive the rows and 4 wires that drive these. When you punch a button, you connect one of the column wires with one of the row wires. So this looks real straightforward, right? Turns out it's not straightforward at all. It's actually rather complicated. And what happens is, for starters, when you make these inputs, these buttons, these wires aren't attached to anything except the upper surface of the membrane pad. So they're basically floating. So as a result, you've got to put pull-ups on all these, or pull downs, or whatever you're going to do. You can do it either way, but you have to do some kind. You have to put pull-ups on those. You have to put pull-ups on all these, or pull downs. So you have to hook them up with pull-ups. So that's one problem. And then you have to scan the pad. You have to scan the row lines and read the columns. Scan the column, drive the columns and read the rows. To do that, you have to switch the tris bits, from 0 to 1s and 1s back to 0s. And so and you have to do that fairly quickly. In addition to that, you only have to scan one axis, and as soon as you detect that there's a push, then you can scan the other axis. And then you want to continue then you want to wait until there's no push before you go back and record another push. So really, there's a bunch of logic to making that work right. And it turns out that figuring that logic out is challenging for students. This is one of the areas. There's some people naturally gifted at this, but most people struggle with this. And so this is one of the things, this is one of the skills that you need to be developing. And partly doing this project kind of pushes you along that path a little bit. And as you do other projects next fall and next spring, whatever, you'll hopefully develop more of these skills. So don't recoil from this challenge. Embrace it. Because this is stuff you need to learn. You need to learn how to think through these problems and figure out a logical, stepwise solution. And it's a little bit painful learning it. But one of the ways you should do it is in your mind, create a little block diagram where you kind of diagram out different ways of how you're going to do it, and just think through the logic. And it really is helpful to draw a little block diagram out, and then and what would really be ideal, but it's actually never happened, is if a student would work out a block diagram and then bring it in and say, does this look reasonable? Instead, what people do is they come up with all this crazy, convoluted, unbelievably complex, and commented out multiple parts code, and say, how come this doesn't work? And as you can imagine, debugging this is really difficult. Usually you just have to throw it out and start over. Debugging a block diagram is a lot easier, because I'm not worried about voltage levels and stuff. I'm just worried about, okay, have we covered the basic steps? And when you get that lined up, it enables you to sort of launch yourself to then begin to write the code to implement your logic. It's much better to get the logic in your mind first and then do the code than it is to do the code and then try and figure out how come it's not working. Because really, people can actually write code that is so incomprehensible that nobody knows why it doesn't work. They just know it doesn't work. And rather than figuring out what's wrong with this code, it's much better to figure out what right code would look like. So sometimes we ask the wrong questions. And so I encourage you to really discipline yourself to think in terms of a block diagram first, because that'll really help you. And the other thing is, you should kind of do this. You should take advantage of the team. On your team, you'll have people probably that have sort of different skills, and so have somebody who's maybe good at thinking this through, draw it out, and then the other team members who may be good at sort of kind of logically thinking through it. They can kind of see where there might be some flaws, and then you can refine it. And so once you get your logic kind of in your mind, this is how the system should work. Then you have some other issues to deal with. One of the things is you may have some sensors. So the sensors, so there's all sorts of issues with the sensors. We want to interface these sensors to the micro. And when we interface them to the micro, we have some issues. One of them is we need to know signal levels. And then we need to know, type of signal. So is it going to be analog? Is it going to be digital? And if it's analog, do we have to condition the signal to get it to read it? And then how fast? Frequency. There's various other ways to describe this, but how rapidly is our signal changing? And one of the things you'll find, you can immediately know that your processor is not going to be able to cut the mustard if it's having to process things at gigahertz levels when it only runs when it takes it a full megahertz or a full microsecond to do a single instruction. So you know it can't keep up with a gigahertz signal. So then you have to think about, well, maybe I need an external device, or how's that going to work? And then you have to think about, are my signals, if they're digital, what's the protocol, okay? Protocol. And if you're thinking about the protocol, then you have to ask yourself, well, do I have a built-in module that handles that protocol? Or is this a protocol that I have to create the module for in software, so-called bit banging? So that's where you have to write your own code and your own timing loops and everything like that. And there's a whole bunch of sensors that are like that. They require you to bit bang. The one-wire sensors, the Samsung infrared remote controller code, the real-time clock sequence, and a bunch of stuff. And then there's some sort of mixtures between that. Like, for instance, if you want to, is anybody interfacing a GPS module? I don't think anybody is. If you're interfacing a GPS module, so it sends its stuff in UART. Okay, that's great. You've got a UART module, but the data is encoded. So it's encoded in an ASCII sentence, and you get, in fact, there's like, I don't know, 15 or 20 different sentences. And so you're only interested in one or maybe two of the sentences. So first you have to detect the sentences that you're interested in, and then you have to decode the sentence. And it's usually a comma separated sentence. So you have to know where in that comma separated sentence the data you're interested in is. So you have to parse the sentence, and you have to parse it with comma separators. And it may be that in some cases there's missing information, so there'll just be two commas and no space between them, which means that piece of data is not present. But then other data is present, and that's what you're interested in, so then you can find it. But you still have to count even those commas that are just next to each other. And so you may have to devise some protocol that encode, even though you've got a module to input the data stream's still encoded, and you still have to decode that. So you have to think about all these things with your sensors. What about voltage levels? Is the sensor need 5 volts and you're going to run at 3.3? That's one of the reasons we made this new board with 2 voltage regulators, one at 3.3 and one at 5. So you can easily switch back and forth. However, you may be in a situation where you have 2 sensors, one that needs 3.3 volts and one that needs 5. And then now you're kind of screwed. You have to pick one and then work out the other. And usually you can do that. A lot of these sensors are 5 volt tolerant or 3.3 volt tolerant, so you can kind of work across it, but some of them aren't, so you have to kind of pay attention to that. And then many of the sensors have to be set up. So for instance, some people are using the little 128 by 64 OLED display. That's I2C. The interface is I2C, and that's great. But the problem is, I don't remember the exact count, but there's something like 30 registers that all have to be set with initial values before you can use this thing. So you've got to write 30 registers on this chip, and nothing will happen until you get those 30 registers written. And they include such things as the voltage levels driving the brightness of some of the little bins, and it's really pretty impressive. But you have, and of course, you might be able to do things like scroll the display and flash it and things like that if you change these registers. But initially, all you want to do is just get it working. And so what values have to be in there? The data sheet's indecipherable. So now you have to go out on the web and find somebody else's code and then adapt it to your situation. All sorts of things. So it's, and then it turns out the splash screen, oh, well, that's another thing. So it requires a certain BMP, and then the BMP has to be properly formatted. So then you get some kind of an illustrating routine that lets you draw the picture, and you have to figure out how big to make it so it's right. And then you have to process it with another routine that gets it in the right format for the splash screen, so it'll be properly byte registered and set up so it displays. And you have to find all those routines and download them and get them installed. Can be a lot of work to get simple things like that done. And that's the kind of stuff you're going to be doing routinely. Okay, so anyway, so you have sensors, and then you have logic. And then you're going to start thinking about your code. Okay, so as you think about the code, there are a number of things to think about. Now, one of the things that happens is, one of the big problems, so in the old days, and maybe even still, our senior design teams, we would see this all the time. They wanted to have oh, I don't know, 3 or 4 different kinds of sensors, and so they'd get an Arduino and they'd find a program that would interface sensor A, and so they'd hook up sensor A to the Arduino, run it, everything was fine, because all the code was out there. They just downloaded it. And then they had sensor B, and so then they got another Arduino and they hooked up sensor B and downloaded that code, and that ran fine. And then sensor C, they got sensor C and they hooked it up to a third Arduino and downloaded that code, and everything was running fine. And then they wanted to put it all together. But the problem was that when they tried to integrate the modules, they couldn't figure out how to do it, because the modules were, maybe there were collisions between pins. How do you deconflict that? And so then they would go down and try and understand this code. Well, this code would have a library here. Maybe it would have a library here for maybe the OLED display. And then, but that uses I2C, so that's called the I2C library. And then that required another library to provide the GPIO drivers, and then that required another library to do some other stuff. And by the time they were 4 or 5 libraries down, just to understand 3 lines of code over here, they were so confused they couldn't do it. They simply could not take those 3 different programs and integrate them into one on one Arduino. So for that reason, Arduinos were actually outlawed as sort of your primary processor for senior design, at least by Dr. Allen. Okay, so that's fine. Well, so with the PIC, the advantage we have with the PIC is, the disadvantage we have with the PIC is we have to write our own code. Although there's plenty of code out there, but there aren't these built-in zipped up libraries that you know exactly where to find them. You just download them, install them, and then you hit a button and bang, your software is done. It doesn't work like that. You actually have to write some code. But at least now you understand your code. So, but even with the PIC, we have the same problem. So let's say one group wants to, let's say they want to use a 2x16 LCD display, and they also want to use the touch buttons. Okay, well that's great. We did a lab on touch. We did a lab on the LCD, but some of them may share pins. There may be a pin that we use with the LCD that we also use for the touch, or maybe it's something else that conflicts. So now we have a little problem. So one of the things when you do your code, you've already got your block diagram and you've kind of thought about your interfaces, so you've got that all worked out, but you still need to deconflict your resources on your microprocessor. So the microprocessor has limited resources. Now you can always get a different chip, but in this case yours is soldered on, so you're kind of stuck with that chip. And so it's pretty powerful, but it's not the ultimate. So what you have to do is you have to sort of plan your resources. And normally what you want to do, as much as you can, is you want to set especially the tris registers, the AND cell, you want to set those in a single config file. So you want to plan your resources, and you want to create a single config file that you're going to call at the beginning of your program. And if you want to make a change in one of your configurations, you'll do it in that file. So in that file, you have tris ABC and add cell ABC, and maybe you initialize the ports, and you have everything kind of all set up in that config file, so that if you need to change something, you know you have to go to that file to change it, and you know within that file you comment all your settings. So if you change something, you only change the bits you're interested in changing, and you don't write a zero. You don't zero out the whole tris-C register when you want an output on RC2, because you may need RC5 and 6 to be inputs, or you may need some other configuration. So you do want to pay attention. And if you do this all in a single configuration file, and then you comment it, well, so you know how everything's set up, then hopefully you won't have the problem. Now, some things like this touchpad, where we have to switch the tris bits for the rows and columns from inputs to outputs and back and forth very quickly to scan it. Okay, so then you are going to make changes, but then you just annotate that in your configuration file. You can say bits, RB 4, 5, 6, and 7 are going to be controlled by the software that's scanning the membrane pad, and also C7654 are also going to be changed. But the other bits are going to be left alone in those programs. And so we'll still configure those in the configuration program. The other thing is, so you want to do that, and then you also want to finish up, you also have modules you're going to use. And so you want to go ahead and configure all your modules for, for all their configuration registers. You want to get them set up so they're going to do what you want them to do. And there are some times where the data sheet's just not simply clear enough to read it and, okay, we're good to go. In fact, I hate to say it, that is the rule, not the exception. The exception is that you read the data sheet and it's clear what to do. The rule is you read the data sheet and you're still confused, and so then you read the data sheet 4 or 5 more times. So many times what you actually have to do is break some of these functionalities out and just deal with one module at a time, configure it, make sure it's actually working, and learn how the nuances of its configuration choices work out. Sometimes you can use Microsoft Code Configurator, and you can configure it in that, and then you can actually look at the code that it generates and see how they set it up, and then that'll give you a good idea of how to set it up. Okay, so in addition to that, most of the time with your modules, you want to create all the settings in an init routine, an init function. And you want to put all the settings for a module. Now, for each module, you might have a different init function. So you might have an init UART, you might have an init A to D, you might have an init touch, or whatever. It's always really good to do that. And that way, if you don't want that functionality in your program, you can just delete that module or that function and delete the relevant code, and you don't have to worry about combing through your other configuration files and figuring out where you had to set things correctly. And within these modules, again, if you have to set configuration bits like tris and ancel bits, you should go ahead and do that, but you should do that in such a way you only affect the bits required, and then you should go back to your config module and annotate that on all the appropriate settings, so you're aware when you start screwing with tris bits and ancel bits in your config file that some of them may be modified in these module init functions. And so it's really good to comment that, so you know what's going on. Okay, and then, so this is good, and then finally, there may be a few other things, like the system clock speed, and then in order to use the delay functions, you need the crystal command. I forget what that is, whatever that is. Set it for the frequency of your clock speed. And so there's some other setup stuff. So basically, the first thing you do is you get all your setup, and you get it all in one place. Don't put setup stuff inside of loops that doesn't absolutely have to be there. So if that setup stuff can be moved out of the loop, do not put it in the loop. One of the reasons for that is sometimes when you turn a module on and off, it zeroes out some stuff that you may not anticipate it's going to zero out. And so you just have to be very disciplined. Put all your setup stuff either in a config file for your tris and ancel stuff for your GPIO ports, and then have an init function for each of your modules, and then set up the general stuff like clock speeds, and if you're going to create interrupts, put that in there. Your default settings like crystal speeds. For some of the routines, for maybe the math functions, you may have to define pi, for instance. There's several different things you might have to do in this setup. But just make sure you put all the setup stuff in there. Don't bury it scattered throughout the program. Because when something's not set up correctly, you want to know exactly where to look. You don't want to have to start crawling around in lots of code. Imagine having programs. One of Bob Apolloni's helped us a little with Apolloni's helped us with Micro 2 a fair amount, and they're developing a program. Their program, I think it's 2 million lines of code. When you have 2 million lines of code, do you think you can go looking for where you might have changed a register that you're maybe set differently someplace else? You cannot do that. That's just insanity. You will lose your ever-loving mind if you create that kind of situation for yourself. So you must be more disciplined. Now, our programs are small and simple. You can kind of get by with it. But even in these programs, I have seen many a student, get burned because they didn't have a configuration function where they set the tris and the ancel bits. They had them scattered throughout the program, and in one line they cleared them, and another line they set them. And they thought they were cleared, but actually they were set, or they thought they were set and they were actually cleared, or maybe some were correctly set, but the others were wrong. So it's really important to do it, to be more disciplined about this. Okay, so once you get the setup, all this is set up, that's really before you've even begun to implement your block diagram. Now, after the setup, generally speaking, the next step is to break out into functions all the things you can. Anything you can put in a function, you should put in a function. And the reason for that is because you can debug that function and get it working, so then you know your function's good, and you don't have to worry about that part. Then you just have to worry about the rest of your logic. And so identify the things that you can generate as a function. Like, for instance, you can create a function for this number pad. You can create a function to scan the pad. Or you can create a function to scan the touch buttons. Or and basically then it'll give you the touch button that's touched or the membrane button that's punched. And then you can create that as a standalone function, debug it, and fix it. You can even assign that to a different member of the team. And all he'd have to do, or she, would be to tell you what the required settings are for the configuration bits, and any modules that are used, create an init function for those settings, and describe specifically what the tris and the ancel requirements are, and annotate that, and then write a function. And then that could be a standalone program, fully debugged, but you can still integrate it because you've laid out the resources that it uses. And then if there's a conflict, then ideally, what's really nice when you write these functions, if you do pound define, like row 1, that could be like RB3 or whatever, and you can change those. Sometimes it's nice to be able to do that. Sometimes it's a little more coding. But ideally, if you spend a little more time and code it, you can actually have it set up so that you can change those definitions arbitrarily. Now, sometimes it's nice to put 4 bits in the same register and move them around as a nibble. But you don't actually have to do that. You can actually break them out as individual bits and deal with them individually and make this transparent. So at the beginning of the little module that you write, the little function, you can have an accompanying header file with these defined statements and the function prototype, and then your main routine can just call the header file, and also your C function file can be separately loaded and compiled separately, and just linked all at the end. And that's really nice. Once you get that all debugged, then you can just provide those 2 files to the main routine. So there's a lot of features that have been created to make this fairly easy to do. And it's so much more robust when you program like this. Okay, so now we're going to do the loop. Okay, so So now you're going to do a loop, and when you do the loop, you basically for loop. So this is going to be the big loop. So all the functionality of your actual program has to be in here. So where does it start? So if there's like an init message that never gets repeated, you wouldn't want that in the loop. You have that outside the loop. It's part of your setup. But assuming that you're going to get all this done, then here's where your block diagram goes. And your block diagram talks about, okay, I have to read in a value, or I have to scan. Say, I scan the rows and look for a touch. If I see a touch, then I'll save that row and I'll scan and I'll switch my tris bits around and switch I'll drive the lines that I need to drive. I'll switch that around, and then I'll read the other lines, and then I'll save that value, and then I'll assemble them into a maybe an 8-bit byte, 2 nibbles, and then I'll send that value out to maybe a function or a switch statement or whatever, and it'll return the key that I press, and then I'll do whatever I'm going to do with that, and then that completes it, and I start the whole process over, or whatever. And many times for simple things like a button punch, or a keypad press, or a touch button sense, you many times have to scan till activated. Okay, save result, and then scan till not activated, and then usually a small delay. Now this is usually how you have to think about it. Scan till it's touched, punched, or whatever. Save that immediate result. Then maybe in the case of the memory pad, you have to scan the other. You have to maybe you're scanning the rows. Now you have to scan the columns. Save that result. Scan the column. Save that result. And then keep scanning until it's not touched. And then when it's not touched, wait just a little bit, and then you can go back. You can do something with the result down here, the final result. So take action, and then you start the process all over. And the reason why a lot of times you have to scan till it's punched and then scan till it's not punched is because because you're executing instructions, maybe you're scanning a button 20,000 times in a second, or maybe a lot faster. It depends on how tight the loops are. Remember, you're able to execute 1 million instructions a second at the 4 megahertz clock that we routinely use, and you can actually use the 32 megahertz clock, and you can actually scan 4 million instructions a second. So, not counting branches and stuff. That's a lot of instructions. So you can scan some of these pads very quickly, and as a result, you may detect 1,000 punches when really it was supposed to just be 1. So that's why you have to scan, and then, well, just a lot of things. So you have to think. You always have to think through that your machine is running a lot faster than you normally imagine things, and because of that high-speed change, that high-speed activity, it's easy to misunderstand how your computer is going to process some sensors input. Okay, so and then when that's all done, you sort of need some kind of you may need some kind of a final action, something that sort of cleans up your results or saves what you need to save or whatever, and then your program's over. But normally, for the kind of stuff we're doing, we normally really just have this a big setup part and then kind of the loop part. And that's a good way to think of it. That's kind of how the Arduino sketch thing was set up. They use a preprocessor. It is C, but you have to write a setup function and a loop function, and then that translates them into the initial code and then the infinite while loop, basically, and puts it all in one function called main. Okay, all right. I think I'll stop there. I wasn't maybe going to talk about FETs, but I think I'll do that next week. We'll have another demo. So we have. So let me just say. So this week we have our. On Thursday demo day. So everybody has to be there, and the mandatory time, I want everything ready to go, if at all possible, at 4 p.m. So try and get try and have, if you have a class, try and hustle, maybe see if you can get permission to leave a few minutes early from class, or get your other teammates to get things set up. Yeah.
How early should we show up? We can show up first.
Yeah. So we'll have use of the facility probably 2 p.m. even earlier if you want. But I'll try and have Anshul there, say at 2, to kind of help, to give you pins and kind of, we'll try and put team numbers on the tables and the bulletin boards. Yeah.
As far as the lab report, do we have it with us that day?
No, that's okay. Yeah. So as far as all I really want you to do for this, I just want you to submit the code at the end.
Okay, so don't do it.
Yeah, you don't really need to do a whole lab report.
Okay.
Yeah, I mean it'd probably be a good thing. Yeah. But did I have that on Blackboard? I didn't think I did.
Yes.
Ah. Okay. Well, let me look at that. Maybe that is a really good idea. I will tell you, in the real world, it's all about reports. That's really the sad thing. And I know. So let me see what that was. I
know that they're more professional. That is so brutal.
All right, let me look at that real quick. Okay, well that's coming up. So any other questions then? So we'll go until I'd like to go long enough for everybody to have. So I want to go through and judge everybody's, and I'll hopefully have Brandon go through and judge everybody's too. I don't know if you guys know Brandon, he's one of the graduate students. And then there'll be some of the professors that will probably help. I'll have Anshul go through and kind of look at everything too. And I'll also have Ryan do that. So hopefully we'll have about at least those 4 people will hopefully see everything. And then we'll have input from some of the other professors, hopefully. Some professors are real good about always doing it, some professors don't. But they usually don't get through all of the projects, and so I have to kind of correlate scores, and then you have to normalize them because people give different ratings, and that gets really complicated. But anyway, but that's what we'll do. So we will have prizes, and typically we have about $200 in prize money. We'll distribute between first, second, and third places. Sometimes we have ties, which dilutes the money a little bit, but we'll see. In the old days, I used to take $100, $200 bills, and I guess I did $100. I cut it in half for the winners, and then I cut the other 50 in 2/3 and 1/3, and then they had to put it back together to get it to the bank. Yeah.
Do we have to do a presentation?
So I'd like you to be at your station during the class time to present to the judges and demonstrate your project.
Should we have like a PowerPoint or like a poster board or something like that?
So you will have half of a poster board. You'll have half of a bulletin board.
Is it going to be given to us? Or
What?
is it going to be given to us?
What's that?
Like the bulletin board? Or
It'll be there in the atrium.
okay.
And then you'll get to use one half, and then the other team the other half.
Is it okay if we take our poster board?
Yeah, if you want to do a poster board, you can. I'm not encouraging you to spend a lot of money on that,
Okay.
but if you want to look sharp, that's fine. You can also just print out 8.5 by 11 sheets and put them up, and that'll work too. But if you want to do a nice little poster, that's fine.
Okay.
You can. Yeah.
So, like, projects like ours where we had work on it and discovered, like, initially, in our case, like, Snake takes too much memory and switched to something else instead of a game. Yes, Pong in our case.
Snake turned into a Pong.
Snake was such a massive requirement on RAM, and these things do not have massive amounts of RAM.
Yeah.
Pong, on the other hand, does not take a lot of RAM,
Yeah.
so it has turned into Pong again.
So as long as if you can store them as constants, you can use the program memory. But if they have to be variables, then that's the problem.
The Snake has to be there.
Yeah,
It
okay.
has to take up a lot of space. It's too much stuff.
Yeah.
So, we're working Pong. I'm just saying, like, our original concept with Snake, we didn't realize when we wrote that up that Snake doesn't work. So, what do you want me to notate on that?
Yeah, so if you've had like a major setback and you want to sort of explain why you had a great project but the one you have now really sucks, sure, go ahead and do it.
the model worked. It was not going to be a great project because it wasn't going to work. This is way better.
Yeah, okay, no, that's fine, I'm just joking. But, yeah, no, it's totally appropriate to present your journey if you want to do that. The only thing I'm requiring you to do is the title slide. But you're more than welcome to put up other, other PowerPoint pages that tell more of the journey. Yeah, that too. You can also just yeah. Yeah, oh, yeah, I was going to look. Okay, let me look.
Also, what were we going to be going
It's in the atrium. The big, when you walk into VSE, it's the big open area. Yeah. This only exists on the first floor.
Oh, wait, no, I know where it is.
All right, yeah. Okay. Oh, yeah, let's see, so this is,
You never
oh, there it is.
signed one, you just put the.
Oh, okay. Oh, yeah, oh, this is nice. Oh, yeah, I forgot about this. Yes, we did create this.
Sure.
Well, so, yeah, so this is really good. So here's what we'll do. I would like you to take a whack at this. I'll give you a fair amount of grace just so you turn in something, okay? But I think what you'll find, is that this is really a nice little template to use. So the reason for this is, when you get out into it, to a commercial setting or really any setting where you're actually paid money to design things, as opposed to paying money to learn things. Okay, so when you're paid money to design things, people really like, because you might drive to work tomorrow and be in a tractor trailer car crash and have your squash messed up and you can't add 2 + 2 anymore, which would be really sad. I'm not suggesting that's going to happen, but and then for some of you, maybe we wouldn't be able to tell the difference. I don't know, hopefully, but okay. So if that were to happen, just think what a bad situation. I mean, it's bad for you. Okay, I get that, and we're all sad for you. But then after we go to your hospital room and we cry over your despicable situation and we comfort your grieving wife and your kids, we go back to our company and we look at what you're doing and we have no idea what in the hell you did. And so you've been working on something for 2 years and we just have to chuck it out the door along with your squashed brain. It's sad, right? We wouldn't want that. So we want you to document what you're doing, and we want that documentation to be really good in case you do have some major problem, or it doesn't have to be that you get hurt. You might get mad and walk out the front door and go start another company and try and compete against us. Which if we didn't put a nice non-compete clause in your contract because we were stupid, you might just very well do that. It happens all the time in industry, and sometimes they have a geographic limit. Okay, you can't compete in the U.S., but you can go to Europe or whatever. Anyway. We would want some documentation so we could salvage what you were doing. And even so, even if you stay around and work in the company for 30 or 40 years, you would not believe how long software that gets written lives. It is amazing. It will live a lot longer than you can ever imagine. And once you're no longer with the company, retired and living in Maui, sipping Mai Tais, somebody back at your company is going to have to maintain what you did. And if you don't document it and leave really good information to make that life easier, they will be cursing you. And you may feel a pinprick in your back every now and then when they stick that thing in their QB-doc, right? So just remember, documentation really is important. Now, I'll admit, this is one of my weaknesses, okay? I'm not a documenter. It's just not my thing. I like to do stuff, but I don't like to write it down. And I understand probably a lot of you are like that. It's a bad habit, you need to break it. And so this would be a good thing to do. But yeah, I forgot we kind of did this. So I'd like you to look through this, do the best you can to create this, okay? So to populate this template with the relevant information. And if you just feel hopelessly lost, give it your best shot. Spend maybe an hour and a half on it. It doesn't have to be turned in this week though. You can turn, as long as you turn this in by the last day of class, it'll be okay. And just give it a little bit of time, say 2 hours. And then I'll be happy with that, and I'll grade it very loving. Okay. All right. So let's stop with that. I'll go back over to my office, and I'll hang around for about 45 minutes and see if.